Is the screen is visible to you all?
Yes, sir.
Okay. So as on the last day, there is so much interaction of the network issue. So that's why we have not connected on the last day. So we have already started in the from the basics of DC machines, right? So whenever we are concentrating about the magnetic circuit, as we have discussed this thing on the last day, that it used the right hand rule, okay? And what is the Faraday's law of electromagnetic induction? That is also we have discussed, E equals to N d phi dt, where N is the number of turns, right? Now, as we know, the magnetic force F equals to N into I, that is number of turn into the current which is flowing through the particular conductor which is on the solenoid. Okay, this part we have also discussed on the last day, that magnetic force for a magnetic circuit, it is given by F equals to N into I. Okay, and this one we have also discussed, that if we consider the resistance for a electrical circuit, so we know the resistance for electrical circuit R equals to rho into L by A, where rho is the resistivity and L is the length of the conductor, and A is the capital A is the cross section. So this is the resistance for a electrical circuit. And L by mu into A. Okay, so ampere turn per Weber. This is the unit. The reluctance of the magnetic circuit is called as ampere turn per Weber. Now move on to the next slide. Now you see this thing. Now we know that magnetic flux density, like it is also called in electrical circuit, it is electrical electrical current density. Similar thing when we are considering for the magnetic circuit, say whenever the flux is flowing, so it is nothing but only for the when the current is passing through the conductor which is given in a solid terms. Okay, if we make the the metal as an electromagnet, in that case the flux will flow from one part to another part, that means from one position to another position, that means from north pole to south pole in the outer circuit, and in between the metal it will flow from south to north. Okay, so that is the flow of flux. And if the total flux is passing is phi Weber, and the cross section of that particular magnet material is A, capital A, that in that case the flux density at a particular direction, that is it will be given by capital B, it is equals to phi by A, that is phi is in now in Weber, and the area of cross section is given in meter square, so it will be phi by A Weber per meter square. It is also called Tesla. Similarly, uh, yeah, in electrical circuit, if we call the electric current density, then current density is given by J. Okay, the current density is given by J, and it is equals to I by A. That means this I is the current which is flowing through the conductor. So the unit of current is ampere. Okay, and the unit of cross sectional area capital A is meter square. So the electric current density is J equals to I by A. The unit is ampere per meter square. Okay, ampere per meter square. Now move on to magnetic field intensity, because this is the introductory chapter, the first module. These things you have to know, and the questions are coming from this seriously topics. Okay, now the magnetic field intensity. Now uh, suppose the wire, the wire, that is the current, the carrying wire that having n turns. Okay, and total current is flowing is I. Okay, so I is the current is flowing. So what is the mmf will be created, that is magnetic force, as we know from this, the magnetic force, that means in a magnetic circuit, the driving force the analogous to the voltage and is called the magnetic force and is designated by capital F. Okay, the magnetic force is created by wrapping n number of turns of wire carrying current I. That means total magnetic force will be n into I. So this is basically creating the magnetic flux. So this is we will implement this thing in the magnetic field intensity, that is given by H. So magnetic field intensity is also having the particular direction, and it is also called a vector. It is a vector quantity. Okay, so with n number of turns of wire carrying current I, the mmf, that is the magnetic force created in the circuit, is n into I ampere turns. Okay, so with I representing the mean path length. So yeah, this is the L basically. L represents the mean path length for magnetic flux. That means the mean path length means, that means, say, if I consider that the magnetic flux is distributed for a particular length, say L, then what is the field intensity at that particular point? Okay, that you have to find out. That is nothing but magnetic field intensity. Okay, intensity at a particular distance. Okay, at a particular position. So what is the length? So the length is L, and the magnetic field intensity is given by H equals to the magnetic force by the length, the mean length L. So Ni by L. So the unit is ampere turn per meter. Okay, ampere turn per meter. Okay. Now there is a relation. There is a relation between magnetic field intensity and magnetic flux density. There is a relation between magnetic field intensity and magnetic flux density, and you know that this is given by B equals to mu into H. Okay, B equals to mu into H. So you can use this formula here. Now you see, for magnetic circuit or electrical circuit, what is the unit? Now, in an electrical circuit, we are considering the potential difference as voltage V. The potential difference as voltage V. Now, the similar thing, the anonymous similar thing in magnetic circuit is called magnetic force. Okay, in magnetic force in the uh, magnetic circuit, and it is given by n into I. Okay, and in electrical circuit it is given by V. So in electrical circuit the potential difference, the potential is V, and similar case for magnetic circuit, the magnetic force is n into I. So what is the unit? You see, the unit is ampere turns. Now, in electrical quantity, electrical circuit, what is the value of current instead of current? So this current is I ampere. If I write down the unit, it will be ampere. Okay, and this for voltage it is nothing but volt. Okay, for current it is I ampere. Now current, so current is a value which is passing through the conductor. Okay, and the same case, if I come to the magnetic circuit, in the magnetic circuit, the which is flowing, current is flowing? No, current is flowing in the conductor, but magnetic motive force is created, the flux is created, and the flux is flowing through the particular way. So in magnetic circuit, the this is the flux. Okay, this is called magnetic flux to flow, and the unit of magnetic flux is wavers. Okay, it's nothing but wavers. Okay, wavers. Now in electrical circuit, what is the resisting element? That is resistance. Okay, so resistance, electrical resistance, what is the unit? Unit is in ohm. Okay, reluctance is in ohm. Okay, and if I consider, about the magnetic circuit, if I consider about the magnetic circuit, it is nothing but reluctance. Okay, it is nothing but reluctance, r, rho, rho r. Okay, roman r. So reluctance, the unit is ampere turn per Weber. So this is for useful for the magnetic circuits. Okay. Now in electrical circuit, the conductivity, is given by 1 by rho. Okay, 1 by rho. And in case of magnetic circuit, the similar thing, the symmetry, it is given by permeability. Okay, that is nothing but mu. Permeability. So unit of permeability is Weber per ampere turn meter. Okay, Weber per ampere turn meter. Now current density. Current density instead of in electrical circuit, it is given by J, and you know J equals to I by A. It is given in ampere per meter square. And a similar thing in magnetic circuit. Okay, analogy. This is nothing but in magnetic circuit, it is given by B. Okay, so flux density is B equals to in Weber per meter square, or nothing but Tesla. Now in electrical circuit, the electric field is given by E. Okay, capital E. Okay, it is given by capital E. And in case of magnetic circuit, the electrical field will be similar to magnetic field intensity. And sometimes it is also called, this electric field, it is also called, electric field, also called intensity. And in magnetic circuit, it is nothing but magnetic field intensity. It is nothing but H, and we have seen this ampere turn per meter. Now, what is this is called? This is basically called, analogy. Okay, we are basically doing, analogy. Okay, we are basically doing ana analogy. Okay, so what is the analogy? Analogous, the analogous values of electrical circuit, electrical parameters to the mechanical parameters. So what is the, say, voltage V is analogous to N into I, magnetic force. Current is analogous to magnetic field, flux phi. Resistance R is analogous to reluctance Roman R. Conductivity 1 by rho is analogous to magnetic permeability mu. Electrical current density J is analogous to magnetic flux density B. Electric field intensity capital E is analogous to magnetic field intensity H. Okay, this is nothing but the analogy. Now we'll move on to the next slide. We'll move on to the next slide. Now this is the basic diagram is mentioned, circuit diagrams. Okay, between the electrical and magnetic circuit. Okay, so in electric circuit the current is directly flowing. You see this is a particular path, a metallic path, where in this case the conductor is connected, and if you apply a voltage source, okay, and the circuit is becoming, and this circuit is becoming a this circuit is becoming a closed circuit. Okay, the circuit is becoming a closed circuit. Now you see one thing, whenever there is an open circuit will be there, no current will be flow, but potential difference will be there. If you put if you check the voltage, okay, if you check the voltage, if you put a multimeter, okay, you will get some polarity, okay, you will get some voltage, but if the circuit is not closed, in that case, the current will not flow. So in electrical circuit, you have to close the circuit. So you see, this is a closed circuit. Okay, this is a closed circuit. So this is the path where it is connected. Okay, and I is flowing so through this path. Okay, and here you see say a ferromagnetic material is used. Okay, in this case, say a ferromagnetic material, this is the this is the portion, this is the portion where you have used a ferromagnetic, we have used a ferromagnetic material. Okay, we have used a ferromagnetic material. Okay, and this is a current source, and this connector having n number of turns over making a solenoid, and then it is closed. Now what will happen, the magnetic motive force which is created for this, it will depend on the number of turns into the current which is flowing through the connector. So it is nothing but n into I. So this is a magnetic circuit. And electrical circuit, say this particular this particular path, okay, this particular reason, this particular path has been replaced by equivalent resistance. Okay, replaced by equivalent resistance. So current is flowing, and you know that as per the Ohm's law, I equals to V by R. Okay, I equals to V by R. Now, similarly, in this case, for equivalent circuit of the magnetic force, you see the magnet. This is nothing but the magnetic force. This is nothing but N into I. Okay, this particular thing, this particular thing is nothing but this particular thing is nothing but N into I. Okay, this particular thing is nothing but n into I. So, which is creating the flux phi, this flux phi to flow through the magnetic reluctance path. And as you know, this is a ferromagnetic material. Okay, a magnetic material where you can make this material as electromagnet, and the equivalent reluctance will be considered in Romaner. This is a particular reluctance value. Okay, this is the equivalent circuit. Students, again, network interrupted. Okay. Am I audible to you?
Yes, sir.
Yes,
Okay.
sir.
Again, network interrupted. Again, I'm sharing the screen. If the screen is visible to you,
Yes, sir.
okay. So, um, so what is the difference between electric circuit and magnetic circuit? So, number one, the path traced by the current is called the magnetic one. The path traced by the magnetic flux is defined as magnetic circuit. Number two, the electromotive force. Okay, electromotive force is the driving force in electric circuit. The unit is in volts. And for the magnetic circuit, the magnetomotive force is the driving force in the magnetic circuit, the unit of which is ampere turns. Serial number three, there is a current capital I in the electric circuit measured in amperes. So similarly, there is a flux phi in the magnetic circuit measured in Webers. Serial number four, the flow of electrons decides the current in the conductor. And serial number four, for the magnetic circuit, the number of magnetic lines of force decides the flux. Number five, resistance opposes the flow of current and whose unit is in ohm. And in the same analogy, in magnetic circuit, it is called reluctance. So reluctance is opposed by magnetic path to the flux, and unit is ampere turn per Weber. Moving on to next slide, next comparison. Now you see here, you see here. So R equals to, we know the resistivity equals to rho into L by A, okay, and is directly proportional to I, capital I, and inversely proportional to L, and inversely proportional to the cross sectional area, that is A. Okay, depends on the nature of the material. And if I come to the magnetic circuit, the reluctance is given by S equals to L by mu naught mu r into A. Now this is directly proportional to L, and inversely proportional to the mu is nothing but mu naught mu r. And now this mu naught and mu r, one is magnetic permeability of the material, another one mu naught is the magnetic permeability in free space. Okay, Achha. And it is inversely proportional to the area of cross section, it's A. Okay. Now the current is mentioned I equals to EMF by resistance. Here flux is mentioned MMF by reluctance. The current density rho equals to L by A ampere per meter square. And here, and in case of magnetic circuit, it will be given by flux density B equals to phi by A Weber per meter square. Now conductivity is reciprocal to the resistivity. Okay, conductivity. So that's why it is called conductance equals to 1 by R. And what is the unit of conductance? It is nothing but mho, MHO. And in magnetic circuit, permeance is the reciprocal of reluctance. So if the reluctance is given in S, capital S, in that case, the permeance will be given in 1 by S. That is this. So permeance will be in 1 by S. Now, in electrical circuit, number 10, The Kirchhoff's current and voltage law is applicable to the electric circuit. Now, in case of mechanical one, the Kirchhoff's MMF, the Kirchhoff's magnetic law and flux law is applicable to the magnetic circuits. Okay. Now move on to the next slide. Now, now what is the Faraday's law of? What is the Faraday's law of? There are so many laws of Faraday. Now, in terms of voltage generation, that means instantaneous voltage generation, there are two basic laws are there: first law and second law. Faraday's law of electromagnetic induction. Okay, and in other one, you will see when you will be coming in the fourth year, the earliest subject is utilization of electric power, where you could find there is a chapter that electrode deposition. Okay, that is also given by the Faraday's first law and Faraday's second law of electrode deposition. So that you have to learn in the when you will come in the fourth year. Now in second year for the machines, the Faraday's law. Now we'll move on to the first law. The electromotive force is induced in a coil whenever magnetic field linking that coil is changed. So that means when a flux links the coil, okay. So if there is a change of flux, there is a change of flux position, so in that case there will be a flux cut as per the Faraday's law of electromagnetic induction. So E is given by n d by dt. So there is a flux change. So if there is a flux change will occur, in that case voltage will induced at the coil side. So EMF is induced in the coil whenever magnetic field linking that coil is changed. Now the second law, the magnitude of the induced EMF, the magnitude of the induced EMF is proportional to the rate of change of flux linkage. Now, let's come to second law. The magnitude of the induced EMF, okay, is proportional to the rate of change of flux linkages. So, magnitude of induced EMF, so E equals to n d phi dt. Okay, and this law, if I come from the, if we consider from the magnetic circuit, there is a mutual inductance and self inductance is there. E is given by L di dt. Okay, L di dt. So that particular L value will come in consideration. Okay. Now Lenge's law. This law states that the induced EMF due to change of flux linkage by a coil will produce a current in the coil, provided that coil consists a closed circuit. Otherwise, current will not be developed. Only the voltage will develop, but current will not flow until unless the circuit is closed. So you see, this law states that the induced EMF due to change of flux linkage by a coil will produce a current in the coil in such a direction, okay, as per the Lenge's law, such a direction that will produce a magnetic field which will oppose the cause, okay, which will oppose the cause. Oppose the cause means, what is this cause? What particular thing is cause? Is cause is the voltage which is applied. So this will act in a reverse direction, uh, uh, in the reverse direction of the induced EMF. Okay, so that is the change in flux linkage. Okay, So as per this, it is given by E equals to minus n d phi dt, or you can say in terms of magnetic circuit is electric circuit, it is minus L di dt. Okay. So move on to next. Now, self-induced EMF and mutually induced EMF. Okay. Self-induced EMF and mutually induced EMF. Okay. Self means that voltage generated or EMF induced within the self flux. Okay. Say a coil is there and flux is created. That flux is linked with the only with the own coil. That is called self induced EMF. And suppose in the surrounding there are another set of coil is there, and even that particular secondary coil comes near to the first coil. In that case, the secondary flux will also link with the primary flux, primary windings. So that particular, this is called mutually induced flux will be created. So you see the EMF induced in a coil, the EMF induced in a coil due to change in flux linkage when a change of current flows through the coil is called self-induced EMF. That means the change in current flows through the coil, okay, own coil. It is called self-induced EMF. Now, when a second coil is brought near a coil producing the changing flux, now in this case, EMF will be induced in the second coil due to change in the current in the first coil. This is called mutually induced EMF. Okay, this is called mutually induced EMF. Now you see, it is given as see. This is coil number one. Okay, this is the coil number one, and this is the coil number two. Okay, now the flux it is created here. Okay, this from coming from north south pole to north pole. Okay, so north to south pole, and here also flux is creating. Now this flux is creating with the this coil also. So now you see E1. So E1 belongs to here. Okay, E1 equals to minus N1 into d phi dt, and this E2 will come from here minus N2 d phi dt. Okay. Now, self inductance of a coil. Self inductance of a coil. We know N equals to minus N into d phi dt. The flux phi, the flux phi is equals to B into A. So you know that B is the flux density and A is the cross-sectional area of that particular metallic piece. Okay, so phi equals to B into A, and we know that B equals to mu into H. So we are putting this value here. So mu into H into A. Now instead of H, we know that it is Ni by L. So we are putting this here. So mu into Ni by L into A. So so it is nothing but mu into N into A by L into I. Now we know that E equals to E equals to minus n d phi dt minus n d phi dt. So this n will be coming out here. This portion d dt is coming out here. Remaining portion is phi only. Okay, this phi comes to here. So phi is nothing but mu into nia by l into I. So we put here mu into n a by l into I. So after putting this value, it will be coming as minus mu n square a into by l into di. Okay, so you see, as we know, some confusion may occur in your mind. Sir, why you have written here dit? Because you know, on the last day also I have told that whenever we are talking about the instantaneous value, whenever we are talking about any instantaneous value, this should be written in small sign, which is very well in nature. Okay, so that's why the small e, okay, equals to minus n d dt of mu into na by e by l into I. So as I, we know that this I is the instantaneous value, so it will be coming as mu n square into a by l di dt. So this particular value minus mu n square a by l is nothing but coming as minus into l di dt. That means this l is nothing but mu n square a by L. Okay, this is nothing but called self inductance of the coil. Okay, so this L is called the coefficient of the self inductance of the supply. Okay, L is called as the coefficient of the self inductance of the, or simply self inductance of the coil. This is nothing but self induced air. Now we'll move on to the next slide. Now the some calculation is there. You see that we know that phi equals to b into a. Okay, flux equals to b into, as you know that as you know that b equals to phi by a. Okay, as you know b equals to phi by a. So from here phi equals to b into a, and for b, you know, it is nothing but mu h. So mu h into a. The mu into ni by l, this will be l only. Okay, into a. So from here you can say this is the I, is the instantaneous current. So d phi will be equals to mu into n into d phi by l. So d phi so d phi di will be equals to mu into n into a by l. Now if I multiply both sides, if I multiply both sides by n, so number of turns, so n into d phi di is equals to mu n square a by e, or it is nothing but l, as we have seen from the last one. So equals to, say here, equals to minus un square a di dt, and equals to minus l di dt. Okay, so you see d phi di equals to d phi di equals to mu na by l. So n d phi di equals to mu n square a by a e l into equals to l. So l is nothing but n d phi t Henry. Okay. So as you know, this particular value mu n square a by L is nothing but L. In the last previous one, you see mu n square a by L is nothing but L. So this value is nothing but n only. So n equals to n d phi di Henry. Now if phi and I have a linear relationship, okay, in that case if they are linear, so we can easily remove the very small value. So in that case d phi can be represented with phi, and instantaneous value I, that is di, can be represented with capital I, so the RMS value. Okay, so in that case L will be equals to n into phi by I Henry. Okay, so where L equals to mu n square a by L equals to n into phi by I. Okay, so n will become n square, so it will become n square by L by mu into a. So it is nothing but n square by reluctance. Okay, so students, have you understood whatever we have discussed today?
Yes, sir.
Okay,
Yes, sir.
Yes, sir.
so and stop my recording.